All right, our next problem. This is a problem that's been on exams before, and with mixed results. So what do we have here? We have a 4-pound hanging rod. It's 3 feet long. All right. We have a box here, a small box, weighs 2 pounds, and it's sliding at 12 feet per second, and it's going on a smooth surface, so there's no friction here. All right. And it's going to whack into this bar near the bottom. And so we're told it strikes the end, and we're to assume the block is small relative to the length of AB. Why do we want to do that? Well, first of all, let's just note we're having an impact. So the fact we have an impact says this is an angular momentum problem. So impact points to momentum. Why do we have angular momentum? All right, if we look at AB is in pure rotation about A. A is not moving. Everything just rotates around relative to A. Because of that, this is translating, so we have to use momentum, because this is in pure rotation, we need to use angular momentum here. We cannot use linear momentum for something that purely rotates. All right. So we got our strategy: angular momentum and handling the collision. Now notice it said assume the block is small relative to the length of AB. Why? All right. So this rod rotates about A. So we're going to wind up doing basically using angular momentum, and so we'll have HA1 be before the impact, plus integral sum of the moments about A external dt equals HA2 after the impact. All right, this is the problem term. All right, we don't know enough to evaluate this, so we want to be able to say this term is 0. How do you do that? Okay, well, when these two impact each other, this will push on that and that'll push on that. So those forces cancel. All right, so they don't produce any moment. They're internal relative to A. But here's the thing. So here's G. There's 2 pounds down. If this distance is large, all right, if it's far away, then, so putting it another way, if we can't assume that these things are so close that this 2 pounds is pointed up into A, then we have a moment here. This is we give an external moment relative to A. That's a problem. Okay? Then this is not 0. All right? The other aspect of it is that we're saying the impact, you have your moment, but the impact is so short. So you may have a force that exerts a moment, but when you look over the time period, this is so short that the integral becomes 0 as well. So what we have here is we're assuming that this box relative to this length is very small. So basically G is very close here. So basically this lines up with A. This is basically parallel here, lines up with A. So we're not concerned about that. Note we have 4 pounds here. But that's just lined up with A. There's no moment there. So we're looking at the sum of the external moments about A. They don't apply under our assumption. Okay, so that's why that's important. All right. So knowing that, excuse me. So now we're rotating about A. So this is a slender rod. So we're going to take mass moment of inertia at A. That's 1/3 ml squared. If it was in the center, it would be 1/12 ml squared, but on the edge, it's 1/3. And so there it is, 0.3727 slug feet squared. All right. And so given that, we can now appeal to angular momentum, where I said we're going to be measuring at A. Right here. And so let's make that happen. So before the impact, what do we have? This isn't moving, so that's 0. So we got that. Relative to g as it comes into contact, this term here is r from a to g cross mass times the velocity of g. So if you pick velocity of g is going this way, so r cross v would be positive. So we have 2 on 32.2 for the mass, 3 feet for the r, and 12 feet per second squared for the velocity. And here's another reason why you want g to be small, because you want to be assuming that this is lined up well with the end, this end here. All right. Now, so that's all the angular momentum at the front end. This is a 0. Then on the back end, we have, as the impact happens, this is going to fly away, so it's 0.3727. And I'm going to express this in terms of velocity. So this point B, the 2 refers to state 2. State 1 is before impact, state 2 is after. Divided by this 3-foot distance would give me the omega that would be here. Why did I do that? I need this velocity so I can do an impact equation in a moment. So just allow that. This here amounts to omega. Then we have r cross mv again, so mass. Vg state 2, so the velocity after impact, and then again this distance is 3 feet. Okay, if we look at this, we have 2 unknowns. And so once again, when you have an impact, we appeal to the coefficient of restitution to help solve our problem. So what we have here is coefficient of restitution is 0.8. And so what I'll use the equation this way. So VB2, this would be, here's B, here's G. So velocity of point B post-impact minus velocity of G post-impact over velocity of G prior to impact minus velocity of B prior to impact, which was 0. Multiplying this up to the top, we have this equation right here. It's this equation right here produces this one there. So we have 2 equations, 2 unknowns, and just from this equation you can see why it was important for me to get rid of the omega. That's why I did that. All right, so we can solve for VG and VB2, and all of our answers are right here. VG2, VB2, omega A. Catch you later.